we're going to have a look here at mechanical advantage and levers and how the two are related. So most of us have, unconsciously used the principle of leverage. Anytime we grab a breaker bar to, loosen off a bolt that's being stubborn, or grab a long torque wrench to apply more force to something, we don't really think about it. We just do it. So we're going to kind of have a look at it and kind of explain mathematically what's happening here. So we've got three different types of levers that we're going to look at, broken down by classification. We've got what's called a class 1 lever, a class 2, and a class 3. They're all going to have the same components as far as what we're going to be looking at. So what we're concerned with here is going to be the fulcrum, which is the pivot point. We're going to look at the input, and we're going to look at the output. So this top line here, we're going to turn into a class 1 lever. To make this a class 1 lever, we're going to put a fulcrum or pivot point on it. We're going to have on either end an input and an output. So the fulcrum will be fairly central, or at least falling somewhere between the input and the output. So I'm just going to mark this with an F for fulcrum. I'm going to make this side my input, and then my input direction is going to be down. And with the class 1 lever, because of the central pivot point, my output will, of course, be on the other side in the opposite direction. Right? So there's the three components. We have the fulcrum, we got the input, and we got the output. Now with a class 2, we still have the same components, but we changed the orientation. So I'm going to put the fulcrum at one end, and I'm going to put my input on the opposite end. Now with a class 2 lever, the output is in between the input and the fulcrum somewhere. So we can pick a spot, doesn't really matter where it is, but we're going to make this the output. Now, class 1 lever, input and output are always going to be opposite directions because of the centralized fulcrum. Class 2, the input and the output are always going to be in the same direction. Now class 3 also has the fulcrum at the end, but now the input is going to happen between the fulcrum and the output at the opposite end. So this is going to be my input, and my output is going to be at the end. So some examples of these that we see in automotive all the time. Most people think of a teeter-totter when they see this, right? We don't typically use teeter-totters in automotive, but we do use pry bars, right? So the pry bar, you got a long handle, you've got a dip near the end, which would be your fulcrum, and then you've got the part that you put under whatever you're prying on, that's your output. Class 2 lever in automotive would be something like a brake pedal or a clutch pedal, right? We would have our fulcrum up at the firewall, right? The output would be the push rod that acts on the brake master cylinder or the clutch master cylinder, and the input would be your foot, right, down at the pedal. Class 3 lever in automotive, this would be like an engine hoist or a cherry picker, right? So on the top of the crane, we'd have our fulcrum. We would have our input, which would be the piston, and then we would have our hook for lifting on the outside here. Right? Now, in order to use these effectively, we have to have what's called mechanical advantage. And what mechanical advantage is going to do for us is basically multiply the force that we put into it, so we don't have to work quite as hard to do the same amount of work. And like I said before, we've all used this before. And an easy example of it, although technically it's not exactly the same as what we're going to be looking at, it's still pretty close, is if we think about like ratchets, right? So for example, I got a stubby 3/8 drive ratchet here, which is good for, quickly loosening stuff off, but you're definitely not going to be, taking a brake carrier bolt out or something with that, because you're not going to be able to generate the force. Now, instinctively, what you'll do is you'll go to a bigger ratchet, right? What you're actually doing is varying the distance between the output of the ratchet, which is the drive, and the input, which is the handle, right? And we all know, like I said, kind of instinctively, that if we have a bolt that we can't move with this ratchet, we're going to get a longer ratchet. If this ratchet won't work, we're going to go up to a 1/2-inch breaker bar, which is going to give us, a 24-inch handle or something like that. So what we're doing is we're increasing our mechanical advantage by lengthening the distance between the point where the work is being done and the input. So if you look at a class 2 lever, which is what we're going to focus on here, this is pretty similar. The only difference is the output would be somewhere around here rather than being at the head, right? So the actual drive would become the pivot, and the output would come somewhere down here. So of course that's not what we would do for loosening a bolt. But if we want to use a pedal, it works pretty good. So we need to make sure that we have enough mechanical advantage. And if we look at the three things that we have here, we need to throw a couple of extra terms on here. So for the input, we're going to call this the effort. And on the output, we're going to call this the load. And to calculate mechanical advantage, the formula looks like this. So it's EA over LA, where MA is mechanical advantage, EA is the length of the effort arm, and LA is the length of the load arm. Right. So we've already said up here, input and effort are the same thing, right? So if we look at our class 1 lever here, if we're looking for the length of our effort arm, what we would do is we would check the distance between the point of input and the fulcrum. So if we look at that measurement there, and if we just put some arbitrary number on it, let's say this is 4 inches, right? We would have a 4-inch effort arm. Then we'd have to look for the length of the load arm. Now, load and output are the same thing, right? So there's the output. So then we would be looking for the distance between the point of output, right there, and the fulcrum. And this looks to be just a little bit longer. I didn't pay that much attention when I was drawing it, but let's just say this is 5 inches from there to there. So if we wanted to calculate the mechanical advantage of that particular lever, I'll just carve myself out a little spot right here to do it, we would say mechanical advantage equals EA over LA. And if we plug in our values, MA would be 4 divided by 5. And if we go to the trusty dollar store calculator, 4 divided by 5 gives us a mechanical advantage of 0.8 to 1. Right? So what that means is, because my input to fulcrum is shorter than my output to fulcrum, I don't have a whole lot of mechanical advantage here as far as getting more out than I put in. And in this case, actually, I'm going to get less out. 80% is what I'm going to get. So if I wanted to do a force calculation here, what I would do is I would take the amount of force that I want to put in, and let's just say, for the sake of easy math, I'm going to put in 100 pounds. Right? So 100 pounds of input force. I would take my input force times my mechanical advantage, which in this case is 0.8, 80%, equals my output force, which would be 80 pounds. Okay? That's how we do the calculations. And it doesn't matter which class of lever we're using, right? We're going to get a mechanical advantage, or a multiplication force anyways, if we take our input, or the effort arm length, right, the distance from the input to the fulcrum, is greater than the distance from the fulcrum to the output. We're going to multiply our force, right? If we go the other way like we have here, where our input or our effort arm is a shorter distance than from our load to the fulcrum, we're going to end up actually losing, right? What we'll gain is distance, right? So we will move this, say, 3 inches, and we'll get more than 3 inches output, but we're going to lose some of the force. For this next part, we're going to focus in on the Class 2 lever, right? Because we're talking about automotive. This is what we're going to use in pedals. And specifically, when we're doing our Pascal's law calculations, we need to know what the input force on a master cylinder piston is in order to calculate the line pressure or the system pressure. So I'm going to take this here. I'm going to put my fulcrum at the top. I'm going to put my output at this point, which is going to be in this direction. And I'm going to put my input here. This is going to be my brake pedal. Same direction. If we want to know how much force is acting on the master cylinder piston, which again is going to be important for our calculations, what we need to do is figure out what the distances are here. So in this case, if we're looking for our effort arm and our load arm, which we are, right? Because if we just recall our formula here, mechanical advantage, effort arm divided by load arm. And let's use some easy numbers here. So we're going to say from the fulcrum to the point of input, let's make this 12 inches. Okay, so that's our effort arm right there, 12 inches long. Then we need to know what our load arm is. So I'm just going to go from this line right here to this line right here. We're going to make this 3 inches. Right? So now if we expand our formula out, mechanical advantage equals 12 divided by 3. Therefore, we're going to have a 4-to-1 mechanical advantage. Right? If we want to put this into a force calculation, and again, we can use really easy numbers, the formula is going to go like this. Our output force equals input force times mechanical advantage. Right? So output force equals whatever we want to put in. And to be easy, let's say 100. Right? So we'll say 100 pounds in. So our output force is going to be 100 pounds of input multiplied by our mechanical advantage of 4. Output force equals 400 pounds. So why do we want to do this? Right? Why do we want to do this for a brake pedal or a clutch pedal? Well, the idea is if we can pick up mechanical advantage with our pedal, the driver doesn't have to push as hard. Right? Basically, that's it. It makes it easier for the driver to push. We do have to be careful, though. We can't go too far with it. Right? If we go too far, we're going to put a monstrous amount of force on the piston, and then we don't want the brakes grabbing, and every time you step on the brake pedal, you don't want to go through the windshield. So that's up to the engineers to figure that out. We're just worried about the math at this point. So every class of lever, this is calculated the same way, but like I said, we're going to focus on our class 2 lever. We got our fulcrum, we got our output and our input. Right? So this would be the length of our effort arm. This would be the length of our load arm. All we got to do is do the math, and then we can apply that. So the one thing that it's just important, I'll just mention it to make sure you don't get screwed up here. When we're taking this and we're moving it over to Pascal's law, right? The output force I'm talking about here is the output force at the pedal assembly, right? Which will become your input force at the master cylinder, right? So we just got to make sure that we keep that straight so we don't get screwed up. Now, the next thing I want to do here is do like a real world example of this, right? Just to prove it out, just to see that it works. So I built a little bit of a model with some stuff I had laying around. I took a paint stir stick that I had in the basement. Now this thing is 12 inches from end to end. So what I did is I marked off an inch from either end to bring the entire thing down to 10 inches that we're going to be looking at. I drilled a hole over here. This is going to be our fulcrum. And I drilled another hole here where I can hang a weight from. So between those 2 points, right between the fulcrum and the input, which is going to be our effort arm, we got 10 inches. And then I put 2 additional holes in. These are both going to be outputs, right? And we're going to vary it to see what happens. So our what I'm calling load arm 1, from the fulcrum to the output, we've got 3 inches. And for what we're going to call load arm 2, from the fulcrum to the output, we got 5 inches. Okay. So I've got a little block with a screw in it that we're going to mount this on. I've got a little food scale so we can measure the output force. And I've got a weight that I'm going to hang on here. And we're going to see what happens. So the first thing I want to do, though, is calculate our mechanical advantage for each one of these. So if we start with load arm 1, we're going to go mechanical advantage. I'm just going to put in brackets load arm 1, so I remember what we're talking about here. Formula is not going to change, right? It's still going to be EA over LA, right? So effort arm, which is the 10 inches, over load arm for LA1 is going to be 3 inches. So we plug our values in. Mechanical advantage equals 10 divided by 3, which is going to give us a mechanical advantage of 3.33 to 1, right, for that first position. When we look at the mechanical advantage across load arm 2, MA load arm 2, just so I don't get confused, equals EA over LA, right? Formula is not going to change. So mechanical advantage 10 again, right? Because our effort arm is not going to change here. But in this case, it's going to be divided by 5, because that's our new output point right there, which is going to give us a mechanical advantage of 2 to 1. So what we're going to expect to see is the amount of weight that we have as an input. When we hang it from this point here, with a 2 to 1 mechanical advantage, we should see double the weight. And when we hang it from this point here, what we should see as an output is about 3 1/3 times the weight. So let's mount this up and hang weight on it and see what happens. So we're going to prove out some of the math that we did with our mechanical advantage formula. I've taken my makeshift lever here and just attached it to a block so that I've got a fulcrum. And then I drilled, obviously, the holes between our load arm 1 and our load arm 2 so that we have 2 places to attach an output. I'm going to use a food scale here. This is kind of cheesy, but this is what I had around. And I'm going to use some impact driver bits as a weight. So the idea here is we're going to weigh our input force, right, in grams. And I wanted to use a nice easy number. And this is pretty close to 100 grams. I'm going to call that 100 grams. I think even if I tap it a little bit, we'll probably get it closer. Whatever. If this were 100 grams and we look at our mechanical advantage with where we are going to put our outputs through load arm 1, we would have our 3.33 to 1 mechanical advantage, and spot 2 would have our 2 to 1 mechanical advantage. So what we would expect to see is, with 100 grams in, about 200 grams out at the load arm 2 spot, and we would expect to see about 333 grams output at the load arm 1 spot. Now, it's not going to be perfect for a couple of reasons. Number one, that's not exactly 100 grams. Number two, this is a pencil and a ruler and a hand drill. So it didn't make this in a machine shop, right? It's thrown together pretty quickly. But they should be pretty close to what we see. So what I'm going to do here is I'm going to take this off, and all I'm going to use for an output is an Allen key. So we're going to swing it around, and I'm going to go in the load arm 2 spot first, which is going to be our 2 to 1 mechanical advantage. So I'm going to tear that to 0 the scale, and I'm going to clip the weight onto the lever and bring it down. Right? So we expected to see about 200 grams output, right, with a 2 to 1 mechanical advantage. We've got 203. Like I said, the placement isn't exactly perfect. Now, if I don't change the weight, but I do change the output to our 3.33 to 1 mechanical advantage, and I put that back down, we expected to see about 333 grams. We got 340, right? So what's happening here is, the closer I move the output to the fulcrum, right, the longer, I'm changing the ratio between the effort arm and the load arm, right? So basically, the more space I put between the output and the input in this type of lever, right, in a class 2 lever, the higher my mechanical advantage is going to be. And this is what we're trying to achieve with a brake pedal or a clutch pedal, right? We want a high mechanical advantage because what it does for the driver is it reduces the amount of pedal effort that they have to put into it to get the maximum output. And we want the maximum output acting on the either the clutch master cylinder or the brake master cylinder piston, right? So in a car, what we would see is this would be the pivot point up at the firewall, right? The output here would be the push rod that would work on the primary piston of the master cylinder, and the weight that we have hanging on here would be your foot, right? So that would be the brake pedal or the clutch pedal, if I just roll this down a little bit, acting on the input side of that lever.